is additive manufacturing, or also known as 3D printing. And as I mentioned earlier, if you do send a chat, if somebody could kindly read that to me, I'd appreciate that. And when I'm finished with this, I'll take myself off a presentation and go on camera and then answer a few questions. So basically, we're going to cover two sections, but answer three fundamental questions, or these are the key takeaways. And so I'm going to go into this, with the golden rule of know thy audience. I'm not really sure what the level of expertise is throughout the virtual room here. So I'm going to suppose that most of you are fairly familiar with additive, but we are going to review additive the first half of this, and then the second half of this, we're going to talk more about standards. And the three takeaways from this are, sure, additive manufacturing shows great potential for aerospace, but there are some limitations. And very fortunately, SAE, AMS, AM standards play a very, very important role, and we'll talk about why. So the first takeaway is additive manufacturing enables lightweight parts, and that's really the objective function here for aerospace, lightweighting. However, the technology is still maturing, as we know. It's relatively low TRL, I would say on the order of 4 to 7 in general. The principle, what we'll call modality, AM modality, is laser powder bed fusion. Yes.
Hi, Bill. Very sorry to interrupt you.
Yes, sir.
I'm just told that this session was actually planned another maybe 25 minutes from now onwards. And as I see, there are very less participants, and I believe just the coordinator called me. After the track 1 session, a lot of people want to join this session.
Yes.
In another 25 minutes. Okay. I'm really sorry. Maybe can we wait for another 25 minutes for the track 1 to complete, and then can we start?
No, I'm completely flexible. I have my morning booked here for you all. So yeah, if that's most convenient, we could start again, and we'll consider this a primer or a preview. So that's fine. As long as, and I guess you guys are the organizers, but I know Shannon, I work closely with Shannon. If he's comfortable with postponing as well, we could slide everything to the right, 25 minutes.
Sorry, I think even in the, Shannon, are you there?
It is as planned at 6:50 p.m. IST.
Right, Shripati. So maybe I think we'll start this session at 6:50, if that's okay, Bill. I believe that was the. No, that's Indian Standard Time, 6:50.
Yes, sir. So in basically in 17 minutes.
Another 22 minutes. Yeah.
22 minutes. All right.
22.
Okay.
If that's okay. All the other participants, we will be starting this session at Indian Standard Time, 6:50 p.m.
Oh, 50. Excuse me, I heard 15. Yes. Okay.
Yeah.
In 22 minutes.
Yes, yes.
Yes, sir.
And if you want to join track 1, you're most welcome to.
What's being presented in track 1?
Today we have right now, I think the session that must be going on right now would be overview of ANSI standardization, roadmap for unmanned aircraft systems V2 and FAA perspective. And then we have one more session actually for all the participants, how to get involved in SAE aerospace standards development. So that must be interesting for the participants from India. Yeah.
Okay. Well, I will, yes, I will stand by here, and we'll resume in nearly 20 minutes.
Yeah, yeah.
Okay.
Thanks, Bill.
Thanks.
Appreciate your.
No, my pleasure. Thanks for the opportunity. Okay.
and defense industry lead at MSC Software, and he's also an organizing committee member of SAE Aero Standards 2021. Okay, we had some very good, interesting sessions today in track 1. I think there are quite a few topics were covered on SAE ITC standardization activities, unmanned aircraft systems standards, and a standardization roadmap for UAS V2 and FAA perspective was the last session that was going on. So again, a lot of standards there, and we also got a glimpse of SAE ITC organization. So Shripati, can I ask you a question? Can I ask you, when was SAE ITC founded? And do you remember how many consortia companies operate under SAE ITC?
Satish, thanks for this question. So SAE ITC is Industry Technologies Consortium. Of course, the 15 main organizations are, we have the SAE ITC comprising of 1,100 plus companies associated with it. And it also has the aerospace, the land systems, and I think off-highway or the
Multi-sector one, aerospace
multi-sector one. So a lot of consortiums, within ITC, and the number of standardization documents which is released by ITC has been very huge. And we had the from the horse's mouth, inviting more organizations to participate in SAE ITC. I think a few members here as well will be interested to really look into it. Thanks for this question. I think even for the first time ever, I got to know how huge SAE ITC is within SAE International as such. Thanks.
Great. Thanks, Shripati. I think today, again, a very quick update on the agenda that is lined up for today. In the parallel session 2, we have 3 interesting sessions. One is from the Aerospace Material Specification Group on Additive Manufacturing by Bill Billman. And then Shannon Jones will take us through, again from the Aerospace Material Specifications Group on Polymer Matrix Composites. And third session would be on G3, Aerospace Couplings, Fittings, Hose, Tubing Assemblies by Joe Beebe. Now, about the first session on additive manufacturing. I think we all know additive manufacturing is a transformative approach to industrial production that enables the creation of lighter, stronger parts and systems. Bill Billman will brief us on the additive manufacturing development. Quick introduction to Bill. Bill is a founder of Aerolytics, a management consultancy dedicated to aerospace materials, manufacturing and supply chain. He started his career in 1995 as an engineer at Raytheon Aircraft. Bill is actively involved with SAE Aerospace Material Specification Additive Manufacturing Development. His industrial engineering PhD dissertation addressed the impact of additive manufacturing on the aerospace supply chain. He also has a BS and MS mechanical engineering degree from Purdue, and he has an MBA and Master of Public Administration from Cornell University. Bill is a licensed pilot and a lifelong enthusiast. We are indeed very happy to have you, Bill, with us today. Over to you, Bill.
Good evening, Satish. Thank you, sir, for that kind introduction. I assume that you all can see my screen?
Yes, Bill.
Okay. And then I will, let's hope that this little gray bar at the top falls away. Sometimes it sticks. I won't use presentation mode because it's been problematic in the past, finicky with WebEx. So hopefully this mode will suffice. And I'll speak for the next 25 minutes or so and then pause and take questions at the end. Thank you again for that kind introduction. We're going to talk about additive manufacturing And the way that I structured this presentation, since I wasn't really sure about the audience, is I'm assuming that most of you are familiar with additive or 3D printing, basically synonymous. We use additive here for the industrial lexicon, if you will, or label here in the States. 3D printing usually means more kind of MakerBot or some desktop printer, something more recreational. So we'll talk about that specifically in aerospace. And in the process, we're going to cover what additive
Bill, did we lose you?
Yeah, somehow it was I was.
Okay. Now we are getting your audio. Please go ahead.
It shows that I'm muted. Can you hear me?
Yes, Bill.
Yeah,
We are
this is
getting
very
your
odd.
audio.
So I don't know that it's the machine's gone rogue. Yeah, it shows that I'm. Just let me know. It somehow it muted me.
No, please go ahead.
So basically, what we'll do is we'll cover the first section. We'll cover additive manufacturing just to make sure that we're all kind of on the same level, if you will. And then the second half talks about standards. So I just want to make sure that we're tracking in terms of what additive is, and in some cases what additive is not. So the firstly, I would like to talk about what some of the key takeaways are. Additive manufacturing shows great potential for aerospace, clearly, but there are some limitations, and very, very fortunately, SAE, AMS, AM standards play an important role. And AMS, for some of you that aren't familiar with this, is Aerospace Material Specifications. We put out our first specification back in 1939. In terms of the aerospace market, it dealt with aluminum, understandably, for aerospace, and we've been developing that model ever since. So kind of the three main lessons or takeaways from this presentation. Firstly, additive manufacturing enables lightweight parts. That's the objective function for aerospace. However, the technology is still maturing. I think we all agree to that. The TRL is on the order of 4 to 7. And that's why standards plays a very important role. Then secondly, the principal AM modality or technology is laser powder bed fusion. I suspect you all are familiar with that if you are familiar with additive manufacturing. And for metals, this represents about 70% of the market. And there's also powder bed fusion for polymers, but it's less prominent. And then thirdly, the AMS-AM committee has published 25 documents with 35 more under development and covering the predominant AM both materials and processes. And this is phenomenal, actually. It's a very, very prolific group. It typically takes about 2 years to release a specification, so there's a lot of work. And of course, any of you that are involved, and hopefully some of you would be interested in joining us, it's a consensus. And a public consensus is tough. So I'll just leave it at that. Again, the presentation is broken up into two sections. First, additive manufacturing for aerospace, and then we'll go into standards. So basically, what is additive? And I would argue there are three fundamental design approaches for AM parts. All support this goal of lightweighting. So the first one on the far left is shape optimization. We call these organic shapes, and you can see the difference between the green part and the silver part. The silver part has some beautiful contours, some nice lines, things that are very, very difficult to machine. But in some cases, you can print something, holes that aren't round or that aren't straight, things that you can't machine or drill. That's phenomenal. It's better represented in the second picture in the middle, this internal lattice structure. You can see this part clearly is printed and cannot be machined. And there's also kind of next generation lightweighting includes foams. So this is another opportunity. And then the third one is part consolidation, and that's the GE fuel nozzle, the LEAP nozzle, but really it's the tip that's been printed. It's probably as big as your thumb. It's a relatively small part, but it was 19 parts that were fused down to a single part. So in essence, additive manufacturing is most effectively used to produce parts that can't be machined, clearly. So what we do is we add material along the structural load path. That's pretty basic. Therefore, the AM business case generally supports increased complex geometry. So this plot here shows cost on the left, complexity on the bottom. And as you move from left to right in increasing complexity, you realize there's this inflection point where all of a sudden it becomes cost effective to print parts and not machine parts. And this is a bit of a, it's a notional graph clearly, but it's interesting because you enter into a realm like we've talked about with things that you can't machine. So there's a part of this chart that isn't represented with regards to that space where you're printing parts that you can't. So single parts, there is a business case that we'll talk about with low volumes, but in general, high volume, simple parts are typically not cost effective. And then this whole idea of complexity is very, very difficult, if not impossible, to quantify what constitutes complexity. Tolerances, complex geometry, number of parts, surfaces. But anyway, this is the general notion. And then in addition to that, there's this business case where if you're printing simple parts, because of amortizing the fixed cost, the non-recurring cost, tooling specifically, additive makes sense for small production runs. And why is that important? Well, that's important for parts obsolescence. So basically the advantage with additive is you don't create tooling. You can just print the part directly in most cases, not all, but in most. And so this whole issue of tooling availability becomes really, really, really important. And that's kind of the underwriting business case for these old military aircraft here in the United States. We have aircraft that the average age is 26 years for the Air Force, so there are a lot of parts that aren't available. This is a bit of an eye chart. I don't really expect you to read all this, but what's important is that we have these four main, as I mentioned earlier, modalities. Modalities are simply technologies. So on the far left, you have powder bed fusion, which uses powder. That's the one that we'll focus on predominantly, and it has all these appellations, SLM, DMLS, SLS, EBM, but really it's powder bed. And then next to that is directed energy deposition, DED, and there's both powder fed as well as wire fed. We won't get into the details of these. I just want to introduce these concepts. And then these other two modalities that aren't nearly as important or popular in aerospace. So if we focus on powder bed fusion and directed energy deposition, in this case wire, these are the two most common modalities for aerospace. And if you look at powder bed fusion, basically it takes an energy source, most often a laser, but sometimes electronic beam, and it melts powder, metal powder. And very, very commonly, it'll be titanium. We'll talk about that a little bit more. But what are the advantages? This near net shape, complex geometry, things that we've talked about, but on the other hand, limited size, small batches, and this whole issue with material source control becomes very, very problematic. On the right, you could see directed energy deposition, which is basically welding. Much higher rates of deposition, but you lose fidelity, so you have to machine in some cases. And then you have issues even more so with residual stresses. Voids and occlusions become a challenge, not to say that you don't have those in powder bed fusion, we do, and that's a whole nother discussion about how to characterize some of these occlusions, because it's not like a casting. Even though we substitute castings for, or additive manufacturing parts, particularly powder bed for castings, grain structure is very different. So in general, powder bed fusion for the engine, it favors the engine, castings in particular, whereas wire fed is predominant for aerostructures and looking more for a replacement for forgings. It's not all roses. There are limitations with additive manufacturing, and really the reason that this hasn't been adopted fully is because we're still trying to understand the physical phenomena. So this shows an example of powder bed fusion, the grain structure, and basically grains are grown, they're crystals in a sense. And the grain boundaries are really, really important because they dictate, these slip planes dictate the mechanical properties of the part. So here you can see at the very, very bottom, this is the Z direction. You have that base plate nucleation where you're starting the growth of this this crystal. And then as that laser passes back and forth and the material melts and then solidifies, it forms these grains. And these interfaces with the powder bed and between the crystals and when it's melted and remelted really create havoc in terms of the grain structure. So it's something we're trying to understand, and that little rendering in the center there shows different types of grains. These powders are small, on the order of 40 micron, which is about half the thickness of a human hair. So these are tiny structures. And this is important because eventually in aerospace, we focus on creep and fatigue. Those are the main failure modes. And so grain boundaries are extremely important. And historically, we used isotropic material and very, very homogeneous. For the most part, it still had a grain, but the grain wasn't as unpredictable. So we're working on that. And part of this kind of next generation, next frontier is in situ process monitoring and closed loop control. That's in the future. So just kind of summarizing this section, this is kind of a rendering of, for this later powder bed fusion, which is roughly 70% of the total AM market for aerospace. There's a company out there that released some data recently that talked about total number of parts. And this is 400,000 parts that have been produced for aerospace. Now, I don't have more transparency than what I'm sharing with you in terms of what constitutes aerospace. For me, it's usually commercial aircraft, let's say aeronautics. In some cases, it's astronautics, and that's important now because of space vehicles. So if we do consider space vehicles, launch vehicles, satellites, especially rocket engines, then as we create this graph, we've got to consider copper and copper chromium and its derivatives. But basically what I did on, this is my work on the right, if we look out in terms of total weight, because weight typically is more, maybe a more accurate depiction, titanium really dominates in terms of the total amount of material used, and titanium's or nickel's really important as well. Realize that nickel is about twice the density of titanium, and titanium is probably twice the density of aluminum. So this puts everything in perspective. But probably what's most important here is that cobalt that they flag is not a cobalt superalloy, but a cobalt chromium alloy, and that's used for the GE fuel nozzle, and it's used very extensively in medical for different applications for the same reason titanium is. But if you kind of put it in terms of weight, it's a small percentage because these parts are really small that we talked about for the tip of that GE fuel nozzle. So these are the materials that we're talking about. Now we'll talk about standards. So as we transition into the standards, many of you are familiar with SAE, but basically there was a vision that was posted called 2035, and advanced manufacturing, advanced materials are strategic initiatives. So I won't go into the general mission and vision or even method, just to say that AMS uses to convene these neutral forums to create consensus-based standards. These are global standards, and the focus now is mobility. So aerospace has been broadened to include, as for example, advanced air mobility, the session that was happening earlier today. So if you look at our timeline, formally the organization AMS-AM, the Additive Manufacturing piece, was created in 2015 based on a tasking letter from the FAA. But prior to that, it was predated by a specification that was released back in 2002 that focused on titanium directed energy deposition wire. We released our first document in 2017, and then it was a recommended practice. It wasn't a standard. The first standard was issued that following year, and that set kind of the basis of the framework for the construct that we use. I don't believe we're going to go into it, but anyway, we built from there, and then we set up a repair committee back in 2019, and then we issued our first non-metals or polymers document, and then we stood up the ITC, and we just talked about the ITC, the data consortium. So in summary, the committee's published 25 documents with 35 more under development. That's an incredible cadence. And it predominantly is metals. 23 of those are metals, 2 are non-metals. The non-metals is it's a Stratasys system, so it's one of the most common modalities. It's called fused filament fabrication. Very, very popular in the polymer space. We have over 550 members from 24 different countries, and a lot of work is being done. So if you look at the constitution of these organizations, I did some research about a year ago, kind of digging into this. We have over 220 different organizations from 28 fundamentally different sectors. And some of these sectors are very, very well balanced. I would argue materials, aerospace OEMs, this includes this whole space tourism movement, machine OEMs, tier 2s and 3s, which are supply chain members that build parts for the OEMs, et cetera, et cetera. So the membership is very diversified, and it's representative of the global aerospace ecosystem. And we have meetings, and we'll talk about that at the very end, that we split between North America and Europe, and then we have ongoing WebExes to tie in terms of updates for these working groups. How are we organized? Basically, AMS-AM has 3 work streams. We have metals, non-metals, as I mentioned, and then I alluded to earlier that we've set up a repairs group. And the repairs group is overseen by Dave Abbott at GE Aviation, that's in the lower right. And then the chair of this overall committee is, Dave used to be the chair. He was replaced after his 2 renewable 3-year terms by Hector Sandoval, who's a fellow at Lockheed Martin. So if you look at the companies on the map or organizations, these are the prominent players in aerospace, with the exception of Siemens. But Holly Duderman was at an aerospace company, and she recently transferred over to Siemens, but they do land-based turbines. The point is that there's active participation from the key aerospace organizations, and NIAR is the National Institute for Aviation Research, which is kind of under the umbrella of Wichita State University. Very, very active in material qualification, particularly in polymers, and that's where they're heavily involved in this polymer space. Polymer mixture composites, Shannon Jones is going to talk about that next. A lot of that material characterization, it's called CMA 17, the handbook. That work is done at NIAR, the National Institute for Aviation Research. So what's a document look like? So this is kind of prototypical documents. Mostly we're focused on material and process, M&P, but not exclusively. There are some other areas in the value stream. So you can see a draft document on the left. And then if you look at metals, again, we released our metal standards. These are kind of the seminal documents, 7000, 7001, 7003. They happen to cover Inconel 625. Which is really, really common in the gas turbine in the hot section. Excuse me, it's quite ubiquitous, along with 718, Inconel 718, and we have specifications around that too. If you look at polymers, I've talked about the fused filament fabrication. We're using thermoplastics extrusion here. We have 2 very, very important documents that have been released in that area, and then these non-M&P related documents, which are still work in progress. We're looking at machine qualification. How do you qualify and calibrate machines? And maybe there's a certification for the installation and ongoing maintenance of machines, but that becomes your basis, because if your machine isn't properly calibrated and in control, guess what? You don't have a controlled process, and that becomes the foundation for aerospace parts. So on the left, I just want to give you guys an idea of what type of, since we're predominantly metals, what type of metals are being qualified and in what form. And so basically, it's pretty well distributed between superalloy, titanium alloy, and steel alloy, and aluminum to a certain extent. So the blue is superalloy. Superalloy, usually these are nickel-based superalloys, but they could be cobalt. We haven't worked with any cobalt yet. Basically, we have 4 that address superalloy, 6 the red, which address titanium, very, very important, and that's kind of the most popular. And then the green is our steels. So there's 17 different precursor material specifications covering these 4 material groups, and then it's about powder, really. There's 1 wire specification, and why is that? It really has to do for 2 reasons. 1, I would say the popularity of powder bed fusion, like we talked about, laser in particular, but E-beam, Arcam, which is part of GE, is another important company in that space. But also the whole idea about the complexity of controlling chemistry and morphology. And morphology is simply the shape, the size, the distribution. We call it particle size distribution of these particles. Remember that I mentioned 40 microns earlier. It varies from 15, 20 microns north of 100 microns. But this is smaller, again, smaller than a human hair. And so if you know anything about powders, any powder that's fine enough, even grain powder can be combustible. So there's powder handling is really, really important because it's a hazardous material and there's profound safety implications. Not to even mention just the inhalation risk of working with this. So what's the process? Using the AMS-AM framework, we need control, but we also need flexibility, and that in lies the prescription and the dance, if you will, with regards to developing a standard. Because if a standard is too tightly controlled, then it drives cost up unnecessarily, and it becomes untractable. If it's not highly prescriptive, on the other hand, then you don't have enough process control and quality becomes an issue. But basically, we try to control that through this process control. It's called the PCD, the process control document. And we step this through data, through these AMS spec mins, and eventually we're going to generate data for handbooks. And these handbooks, they're called material properties databases. They will feed design values, and these design values are what engineers use for margins of safety, and that's what really matters. So you build a part, you want to make sure it doesn't fail, and so you add additional strength to that part more than you assume that it will see during the life of the part. So basically, we're focusing on these what we call S-basis spec mins. They're not nearly as rigorous as the A and B basis, and this is probably information that's too detailed. But what we're doing is just coming up with basic quality control and lot release, lot acceptance. What's important on this screen is that you realize we need to start with a fixed process. That fixed process is defined by this process control document, PCD, and we can have either proprietary documents, which are the majority, because most companies don't really want to share their secret recipes. That's what we're trying to do, strike that balance with standards. Or we could have these public standards to which we refer to as slash sheets. And we're using those in the polymer space. And that's where everything is prescribed. So that's like, you want to make Toll House cookies, look at the recipe. It tells you not only in the ingredients, but the instructions of how to make those perfect chocolate chip cookies. Silly analogy, but it holds in terms of producing these high quality aerospace parts. So then basically, as we wrap up here, there's an important part of the ecosystem has to do with the coupling between the Additive Manufacturing Data Consortium. This is part of the ITC, as you can see in the lower left. This is company members as opposed to individual members for the SAE committees. And we focus on standards. We've talked about that for the last 10 minutes now. And there needs to be a sponsor, and we need pedigree data. That means we need data. We need history behind this data, the provenance, how was it generated? That's really, really important, particularly for powders for the reasons discussed. And then data generation, we're being supplemented by the ITC, AMS, AMDC, and they're facilitating these spec min generations, and ultimately will serve as a repository for some of these data. That has to do with that pedigree data that we talked about. So in closing, we meet frequently, and our meetings are open and free to join, like with all other SAE activities. Well, maybe not all, but at least the standards committees. And we alternate, as I mentioned, between North America and Europe, spring and fall. And we had our fall meeting, EOS in Texas changed to virtual. And then the spring, tentatively, COVID aside, we're going to meet at EASA, which is the European equivalent of the FAA in Cologne, Germany. And you can see some ongoing regular WebEx meetings. So anyway, with that, I would close. Here's some contact information. I'll stop sharing. And then I'll take a few questions, and I'll come off of off of video here. Let me turn on my light so it doesn't look like I'm some crazy man in the basement of some small beat up house somewhere in the hills of Indiana. And thank you all for this opportunity and take a few questions.
Thank you, Bill. Thank you for the enlightening session on additive manufacturing. We have a couple of questions from the members.
Sure.
I'll read out the first one. What percentage or what % of AM parts are currently used in Aero engines, and which material is used the most?
What percentage of AM parts are used in Aero engines? Well, if we use that 400,000 as a metric, I don't have transparency into that information, but there were over 100,000 GE fuel nozzles that were produced, and that used cobalt chrome. But cobalt chrome is not a popular alloy in aviation. It has a very, very high melting temperature, but it's very difficult to work with. Medicals found better uses. Most of the parts are titanium, but what we're trying to do, and I didn't cover this in the presentation, we're trying to transition from prototyping into part production. And we can do that on a one-off basis, but eventually we want to move into serialized production. And moving into the serialized production, that's when there's going to be a huge push into the industrialization. So I can't really answer that question. That data hasn't been shared. The leader in that space is General Electric, GE Aviation. The laggards are Pratt and also Rolls-Royce. For metals, there are tens of thousands, I've heard hundreds of thousands of parts flying on Airbus aircraft, in particular, Boeing to a lesser extent, but they're using polymers, and a lot of these are clips, so they aren't very important. That's not where we're interested. We're interested in life-limited parts in the gas turbine, for example, and the GE NX uses printed turbine blades by it's called Avio. It's an Italian firm that uses tied aluminide and E-beam, that Arcan machine that I mentioned. So these are fairly substantial parts, but I don't know how that breaks down in terms of total quantity. Good question. Thank you for that.
Satish, you're on mute, actually.
Sorry. Thanks. Bill, thank you for that. In the interest of time, members, what we will do is we will send all your questions to Bill, and we will get back to you with those responses, because we'll go ahead with the next session now. Yep.
I agree.
Thank you,
That's fantastic. Thank you. It's a pleasure to meet you all. I'm going to stay around, and I work closely with Shannon, so I'm interested to hear his presentation. You guys are fortunate to have him present. He's very talented. So thank you for this opportunity. I look forward to answering the questions. Cheers.
Thank you. So members, now let us move on to the next session. Let us learn from Shannon Jones, again from Aerospace Material Specification Group, this time on polymer matrix composites. Shannon Jones is a staff engineer in non-metallic materials and processes engineering group at Bell Flight. He is the chairman of SAE AMS P17 committee that covers polymer matrix, composites, associated materials, chairman of the Performance Review Institute Qualified Products Group, chairman of the Composites Materials Handbook 17, task group tasked with developing statistically valid core material properties, and is a member of CMH 17 steering committee. Additionally, he is involved in the CMH 17 community as an acting voting member in the materials and process data review, statistical, and sandwich monitor working groups. He also supports a wide range of FAA-funded research programs tied to the composites. Prior to joining Bell Flight in 2020, he worked at Textron Aviation in non-metallic materials and process disciplines, supporting a variety of structure composites and bonded structure areas. He has a MS in mechanical engineering and a BS in aerospace engineering from West Virginia University. With that, thank you, Shannon Jones, for joining us today. Over to you. The floor is yours.
Appreciate that. And as much as that sounds like I'm involved in everything, and I guess I am, I've come to realize I'm not very good at putting together lengthy PowerPoint presentations on short notice. I had plenty of notice, but because of all the activity and all these things, I didn't have a lot of time to, or didn't take a lot of time to put it together. So I will probably speak to all of these slides at length. Feel free to ask questions as we go, or if you want to hold them through the chat to the end, that's fine. But with that, let's, I guess, jump right into it. So hopefully you're seeing my screen. I'm going to go ahead and stop my video just for bandwidth reasons. So speaking of SAEP 17 as a committee, the reality is this committee doesn't exist without the Composite Material Handbook 17. We are a separate entity, but very much a support entity to the CMH 17 activity. And so that is was previously Mill Handbook 17 for originally started with transparency, so windows and other plastics, and then grew to support fiber reinforced polymer composites. Now there's 6 volumes to that handbook. Volumes 1, 2, 3 are about polymer matrix composites. 4 and 5 cover some ceramic matrix and metal matrix composites, and volume 6 is dedicated to sandwich structures, which is largely tied to polymer matrix, and that was previously Mill Handbook 23. But as far as what SAEP 17 as a committee is here, it is to sponsor and develop standards for the polymer matrix composites that have data listed in CMH 17 Volume 2. So kind of looking through the legacy of the handbook and the involvement with SAEP 17. Originally, the Mill Handbook 17 and then the early revisions of CMH 17 had material property data in them for polymer matrix composites, but that data was not well pedigreed. Some of it was supplier provided data, some was provided by OEMs or Department of Defense projects, but you were never really sure who did the testing, maybe even what the test methods were, if they were standardized or not, how the panels were cured, etc. And so the data that was in those versions of the handbook had very limited utility to an end user because you didn't have a way to know how legitimate they were. So moving forward in time, we had a program here in the States called AGAT, which was a funded program by the government to help revitalize general aviation technology. And that really became the start of what we considered the current state of the art in polymer matrix composites with shared databases. And that is where a lab gets panels built on multiple lots of material across several different panel producers. And then they test all of that and do a bunch of statistical work to generate the basis values that are published in the handbook. Then as a new end user, you could come along and get a much smaller sampling, say a single lot of that material, process the panels yourself, have the testing done or do it in-house. And as long as statistically you could show equivalence to that larger data set, you then had the ability to leverage that previous work without having to pay for it all yourself. Coming out of AGAT, we had several lessons learned, though, one of which was there was no standard publicly available material specifications for those materials. So many times the material manufacturer of the prepreg wrote and maintained those specifications themselves, and they made them available upon request, but maintenance of those was not done by the end users. And also there was no process control documents that controlled how those materials were made, what materials went into them moving forward. And so the next, so AGAT funding expired. That work was all done at Wichita State University through their NIR, National Institute of Aviation Research. And after the AGAT program was no longer funded, as these materials changed over time, the material suppliers would write AGAT, the people that were formerly with AGAT, still with Wichita State, and say, we're changing a component in this resin system. We need to prove equivalency. will you help us? And there was no funding mechanism for that. So that was one of the big lessons learned from Agate. Following that was the development of the National Center for Advanced Materials, NCAMP. It's another Wichita State entity, stood up under their NIRE organization. And the goal of NCAMP was sort of a next evolution from Agate. Along the same time, the handbook developed some requirements that said if you're going to publish data in the handbook, you need to have a publicly available material spec. That became a requirement, and it was also implied that you need to manage changes moving forward with those products. And there was some additional changes to the test matrices and things as we all got a little bit smarter coming out of Agate. But that was the NCAMP model. So with NCAMP, to qualify a material, you have to have a published spec to purchase the material against. So you have to have some sort of requirements in that document to be able to buy the material. The problem is you can't set realistic values until you have the data that you're trying to generate. And so we looked at it from an SAE perspective. Could we release an initial revision to a spec with to be determined values, or cobbled together values based off of the screening data we had that would allow us to procure that material, then go do the characterization and all of the statistics, and then revise the document. And the fear was, if we published a revision, no change document with numbers in it that weren't statistically valid, somebody might pick that up and run with that, and we didn't want that. And so the fix to that was NCAMP decided to write their own internal specs, NMS documents, NCAMP material spec, with those kind of guesstimate sort of numbers to start with, so they could purchase the multiple lots of material they needed to do the characterization. The plan was then, after the material was tested and the data was submitted to the handbook and approved, we would and are writing SAE AMS documents to convert the NMS to AMS for people that want to go that route. NCAMP does now maintain their NMSs moving forward, but it's not a public consortium like SAE is, where anyone can basically join the working group or the committee and sponsor a revision to a document to get through ballot. And so that's kind of where we're at today, current stage with the handbook, and then discuss path forward as we go here. So next slide. So graphically, this is kind of what I just described, where we've got NCAMP up here at the top. They create these NMS specs, they do the testing, evaluate the data, and send it to the handbook. On the left side with the green circle is this composite handbook activity, where guideline sets the testing we have to do to submit data to the handbook. The statistics working group, of course, sets all the statistical treatment methods for that data. The M&P working group has a lot of content about how to write a spec, how to characterize resins and fibers. There's a data review working group that goes through all of the data reports to make sure all the analysis is correct, and if there's need of engineering judgment to override statistical failures and things, or disposition outliers, we do that. And then after a data set gets approved through the data review working group, it goes to a process called Yellow Pages, which is basically how we get updated content into the handbook. And that goes to all the members of the CMH 17 for review. And once it's approved through that, it's basically put into the draft working copy of the handbook that will be incorporated at the next revision. So along with that, to the right in the blue circle is this committee, the SAP 17 committee, that was set up initially to write the material specs to support the materials with data in CMH 17 volume 2. And then the last leg of all of that is this red circle at the bottom, which is the Performance Review Institute. So that is the same people that do the NADCAP work, and they have a separate entity called the Qualified Products Group. And so we have a committee there as well. We do the initial QPL listings for the materials on these SAE AMS specs that require it. And then we do all the ongoing change management. So as equipment is changed, as resins are changed, ingredients, fiber changes, anything that changes once it's listed there has to go through a change notification and change management process. So the end goal of our committee is to have these publicly available AMS specs that are tied to the materials property that is in the composite handbook and then supported with qualified product listings. So as far as where we are as a committee, our membership, we have representatives from the OEMs, of course. We have people that are at the tier 1, 2, and 3 subcontractor part manufacturers. We have representatives from the material manufacturers that make the pre-preg materials and other polymer-based materials. We have a number of SAE staff members. We have people from the FAA and EASA and some other regulatory communities. And then we have a few what I will call subject matter experts, which mostly are retired people from the industry, but still have a lot of valued information and expert experience that we like to leverage. So everybody that participates on this, of course, participates as a volunteer. And we don't necessarily represent, we do and don't represent the companies we come from, I suppose is a fair way to say it. I certainly do my activities with an eye towards how it impacts my employer, but a lot of my work is being done just for the betterment and furthering of the industry in general. As far as membership, last I looked, we had about 288 members. A small percentage of those, about 20 of us, are the actual voting members. I think it's a little over 20. We have about 100 people that are technically mailing list recipients, which means they get notified of our activity. But when we go to ballot, they can't enter any comments or anything, whereas the liaison people can review the ballots and enter comments. They just don't have a formal vote. So it's a relatively large working group, I would say, or roster, with a very much smaller number of active people that are doing the bulk of the work. As far as documents, of course, when I started this, I said we were set up to be a support to CMH 17, which isn't what these 210 existing documents are. After we were active for a while as a committee, we were technically a subcommittee to SAEP, the Polymer Plastics Committee, and they had a number of old specifications that they felt better belonged to P17. And so we inherited probably 180 plus of their old documents. We've stabilized about half of those at this point, which means we don't have to touch them every 5 years. And we had reaffirmed about the other half of them, and we're going through some review on those right now because they're past their 5-year review. The vast majority of those are not, well, they're problematic for me because they don't have qualified products lists, so I don't know exactly everybody who supplies material to them. And because I don't know everybody that supplies, it is very hard to come up with who is actually using those materials. And so as a structural composite and structural metal bond sort of background, I struggle with having materials that don't have managed qualified products lists with them. So these standards are useful in some ways, but not in structural applications as far as I'm concerned. So while they don't get a lot of attention from us compared to the other things we're trying to get done, there is a management aspect of having to deal with all these documents, and we're kind of working with that and through that. My belief is we will reaffirm these other 80 or so of them that need to be reaffirmed one more time, and then we'll move to stabilize them after that. And all a stabilized spec is a standard that you believe is mature enough and not changing enough that you don't need to review it every 5 years. So it's still out there, it's still active, it can still be used. It just takes the workload off the committee to not have to stabilize it or to reaffirm it every 5 years. And if down the road somebody decides it is an important thing and they want to make a revision to it, you can pull it back to active status and then open a whip and go ahead and revise it. So having said that, near term, this is 5 resin systems on the right, the MTM 45-1, TC 250, 5320-1, BT 250 E6, and EP 2202. These are 5 families of materials that were qualified through NCAMP, and we are actively working to get converted to AMS specs from the NMS specs and then get QPL listings put in place. Most of these are sort of traditional, many of them out of autoclave, some autoclave cure polymer matrix composites that were done, and we're trying to get these taken care of and released and out of the way, because the next step for us is this is support for advanced air mobility or urban air mobility, which are these little mostly eVTOL electric vehicle air taxi concepts. And so the SAE as a larger organization has understood this as an emerging market and has a lot of interest in supporting it. And one of the major likely support organizations for that development is the SAEP 17 committee through either faster curing thermoset composites and or thermoplastic composites. Because most of these companies have goals of making thousands of vehicles a year, and a lot of our traditional thermoset composites, such as these on this list, have minimum 60, most of them 120 to 180 minute cure cycles. And at rate, with the size of these structures and the tooling and the cure mechanisms, you can't afford to build thousands of anything a year with those kinds of materials. And so there are some faster curing thermosets that are in development today. I think a lot of them are probably coming out of the automotive sector and being looked at with aerospace kind of structures in mind, and or are modified current aerospace polymer technologies that they're pushing hard to make them cure faster. Some of them on the order of a few minutes, many of them maybe a little bit longer than that, 20 to 45 minutes. And then thermoplastics, of course, has been around for a while. The Dutch have done an awful lot of work with that sort of technology through various consortium, government funded and other academic. And it is implemented on a number of large commercial transport sort of aircraft with other applications coming. The difficulty with thermoplastic for a lot of people is the tooling cost. And in traditional general aviation and other associated industries, you can't afford the tooling cost if you're only ever going to make a couple hundred units of an aircraft with thermoplastics. But that is certainly coming down as you get into these higher production rates. And so it has a lot of advantages in short cycle times and realistically good properties for the kind of utilization they'd have in an eVTOL. And so I think there's going to be a lot more development in that. We do have a couple NCAMP data sets with those sorts of materials in work now that'll be submitted to the handbook soon. And I would expect that to move forward. So this committee will take that on. But along with that, even within traditional aerospace and aircraft, there are other new thermosets with better properties that are being developed. We'll continue to support those. There's additional adaptation of thermoplastic composites. And then there's a number of other new or enhanced material forms that we're also looking at. So as a committee, we've largely been dedicated to thermoset polymer pre-preg systems over the last decade or so with continuous fiber reinforcement. There are a number of materials in what we call chopped fiber, discontinuous fiber, molding compound sort of products that are gaining a lot of interest with some people. So I assume we'll be supporting that. There's been a big effort within CMH 17 to adopt new content geared toward bonding, both of metal, structural to structural metal bonding, as well as composite bonding and then hybrid structure bonding, because that's been an area of concern from a safety perspective for the FAA and EASA. And so with the increased bonding content in the handbook, of course, comes a need for additional support for the adhesives that are used in that bonding. And I believe our committee will be covering those. And then with core materials, we're also doing a lot of work within the handbook to get statistically valid core material properties put in the handbook. And so we already have a variety of old core standards without QPLs in them that a lot of people have used for years, but I believe we'll end up with a new set of core standards with QPL listing requirements that are going to be tied to this new data as it's approved. So that's kind of a brief walkthrough of what we are as a committee and what we're working on. My contact information is there. If anyone has questions or would like to join the committee, certainly send me an email or get in touch with Jeff Adkins, who is our staff member with SAE overseeing this committee. As far as meeting frequency, we have been meeting concurrent with CMH 17, the M&P working group, and the CMH 17 meeting schedule tended to be about an in-person meeting every 8 months. So we would meet 3 times over 2 years pre-COVID. With COVID, we've moved a lot of that to virtual, and there's been discussion of moving it to maybe every 6 months, twice a year, one in person, one done virtually. I'm not sure where that's going to end up, but in the meantime, with all these specs we've got coming with the conversion, I'm trying to get us back on at least every other month meeting of the larger roster, and then the off months of that every other month, a much smaller working group for the people that are actually doing the conversions of those specs, and just as a smaller group to do, just the grunt work of working through all those sort of changes. So I guess with that, I will open it up to questions.
Thank you, Shannon Jones. Members, if you have any questions, could you please drop it in the chat box, chat window. Shannon Jones, so far, no questions. I think we would like to thank you for the insightful session on the polymer matrix composites and the committee and the organization, and also sort of you covered on what to look for in the future in terms of new standards that are going to come up. Again, thanks a lot. We really appreciate you taking your time out to sort of brief us on Polymer Composites Committee today. Thank you.
Absolutely. Thank you for the opportunity.
Okay, members, let's move on to the next session. The next session is actually on G3, aerospace couplings, fittings, hose, tubing assemblies standards by Joe Bebe. A little background about Joe Bebe. Joe Bebe is currently the lead design and certification engineer for the hydraulic and mechanical flight control system on the Boeing Chinook CH-47F program. His engineering product team is responsible for sustaining the design, supply chain, manufacturing, and customer support activities on a 50-year-old continuously manufactured and evolving aircraft platform. He has worked in the aerospace business for 40 years and has extensive engineering experience in hydraulic and mechanical flight control system design. Joe has been an active member of SAE G3 committee on aerospace couplings, fittings, hose, and tubing assemblies for over 30 years and is currently the committee chair. His degrees include a BS and an MS in engineering management from Drexel University. Joe, thank you for joining us today. The floor is open to you now.
Okay, can everybody hear me?
Yep, Joe, very clear.
Okay, that's very good. It's not the most up-to-date computer I'm on. See, I don't have a camera on my work computer, so I have to work on my personal laptop. But that's fine. So welcome everybody to the workshop. Again, I'm the chair of the G3 Aerospace Couplings, Fittings, Hose, and Tubing Assembly. I've been a chair of this committee for the last couple of years. They're coming up on 2 years. but I've been involved in the committee for many years. And this committee has been around a very long time. This was formed back in 1941. So we're working on our 80th year now. And this committee has really been a workhorse for SAE as far as producing specifications and standards in the areas, as presented on the slide here. And we're busy. We always need help. And, I'm pleased to share what the committee is all about, what we're doing, and where we're going moving forward, and hope that the international community can become more involved with this committee and help us in our work. So I guess with that, we can go to the next slide since I'm not in control right now. So what are our objectives? What do we do? And, what is our mission? So we basically develop the fluid standards, and we work on relevant standards and maintain what we have already had released. We develop them, prepare them, maintain them. We have up almost as many as 1,000 documents that have been released. And yes, some of them are stabilized at this point, meaning that they may be useful information, but they're not actually, there's no real need to update that document. And we have requirements within SAE to keep documents current. If they're, not really active, they like to stabilize them and not have to reaffirm them every 5 years to minimize the workload on the committees, not just G3, but other committees within SAE. So we get involved, between the original equipment manufacturers, the OEMs, the suppliers, the processors, and we discuss all aspects of the design of couplings, fittings, hoses, and tubing installations. We get involved in the test requirements, procurement requirements, manufacturing issues, what it takes to maintain these products in the field. And we get feedback from the field and try to address concerns and issues with our standards if we need to update standards, because more often than not, you'll find typos or errors or things that aren't quite clear in the standards, and they have to be maintained and updated. And sometimes these changes happen inadvertently when documents get revised, as I'm sure many of us have experienced. We also, one of our missions is to support product qualification on aerospace standard parts. So we have a group which is primarily the OEM users that review our suppliers' product designs and test reports for listing on qualified products list. So we're really heavily involved in supporting that right now, and as part of the SAE PR Performance Review Institute arm. So the second mission that we have is to really maintain the standards and promote these standards to be used, at aircraft designers or higher level design organizations. And the goal is, by use of these standards, is to reduce the cost of the design, of having to get qualified sources for all the product that is going on to these larger platforms. Reduces procurement costs, makes it easier for our buyers to go out and buy things and not have to get do as much work to get quotes and review quotes and things like that if they're standard parts and they're on qualified products list. And also, just overall maintenance of the aircraft. So we also, as part of our collaboration and preparing and maintaining these standards, we're all sharing with each other, as well as bringing junior technical professionals into the standardization world. They learn from our review of documents, preparation of documents. They're helpful in creating the standards, maintaining standards, and even folks that are not junior technical professionals but maybe aren't quite as knowledgeable about product designs and requirements in the areas of couplings, fittings, hoses, and tubing installations. So we also are involved with other committees. We have 5 committees really with the subcommittees within the main committee, and one is for fittings, the other is for couplings, the other is for hose assemblies, and then tubing installations. And lastly, we have a harmonization committee that we work with our European counterparts to they use our standards, we use their standards, and we collaborate with them and try to to enable each other to use these standards, and that improves aircraft safety, quality, reliability, and again, it decreases our overall costs. And lastly, to do all this work, as we've heard over the last couple of days, is that it's a volunteer organization. So many of the folks are spending their own time off of work hours, and I personally am not a standards engineer. I work for Boeing on a helicopter design platform, and we're responsible for everything from the design to bringing in product from suppliers. And we use the standards. We do develop some of our own standards internally, but that's not my primary function. So it's very difficult for myself and other engineers that support this committee and others to get support from management within their companies to attend the biannual meetings, do project work, and run ballots, and try to get consensus from other users of the standards and developers of the standards. So it's very important that we try to keep company management supportive of these activities. So we can go to the next slide. So some success stories of, there's been many success stories over the 80 years that this committee has been functioning. And, one of the things that we often do is we'll have, the military aircraft community develops a lot of requirements and part standards, and over time, and as was mentioned earlier in the meetings, the military basically wanted to get out of the a lot of the standards business, and allow folks like SAE and other standards organizations to develop standards. So we in this committee were able to develop a lot of standards for 4,000 psi hydraulic systems. And so we have a lot of part standards and performance specifications for fittings and hose assemblies and tubing that we use to develop our own SAE standards that are now in use by commercial aircraft platforms and the suppliers that build those parts. We also I developed a hose assembly and fitting standards for the Boeing 777 when it was going under design and development. And oftentimes these aircraft platforms, they have a need for standards, and they come to somebody like, SAE G3, and they say, hey, we need part standards developed for these, type of products, and, to help us out with to keep our costs down, and, to have competition, to, have a safer, qualified product. And within a matter of, I'd say 6 months or so, we're able to get these designs on paper and get the standards released formally and can be used by the suppliers. So, we're able to actually turn some of these projects around pretty quickly if we need to support some of the new development programs that are out there in the industry. We also recently developed 5,000 psi Flareless fitting and tubing procurement specification and part standards for the Boeing 787 and the Airbus. So A350. It was a very intensive collaboration effort and qualification effort to get a lot of this work done, and it This was kind of a newer design of the flareless fittings, something we hadn't used before, but these modified designs did save a lot of weight and volume on those aircraft, and helped us get the designs out on the street quickly, keep the procurement costs down, and have a good quality product. We recently developed an NAS 5620, which is a qualification testing and material control requirements for titanium tubing. So what we had found in this particular area with titanium tubing and other tubing products is that the AMS committees, they're not in the business of generating material specifications and including procurement and qualification requirements in those material specifications. So in order to invoke some of the unique requirements that we have on titanium tubing for aircraft usage, we had to create our own specification for that, and now have qualified sources for that tubing. So you can't go to folks to procure that tubing that are not approved to supply it. We've also developed a lot of qualified manufacturer lists and qualified products lists over the last 10 years or so for fittings and hose assembly part standards, and we're just trying to develop some additional QPLs for couplings, but we're not quite there yet. There's a handful of the success stories that we've had in the recent years, and there's more to come. Next chart. So some of the work we're doing right now within this committee, what we have within a lot of our procurement specifications is references to other recommended procedures for testing, assembly, installation, where we don't want to overload a given specification where we have standard, test technology or assembly technology. So this particular specification, ARP 1185, is a flexure testing of tubing joints and fittings that we use in qualification. And that ARP 1185, there have been a number of changes in the technology used to perform that testing over the years, and we're trying to update that document to incorporate those particular methods in this document. So that's something we're working on right now. Within the committee for the qualified products, we've struggled over the years with suppliers making changes in equipment and designs and processes, and the industry as a whole and the approvers, specifically the qualification product group within this committee, is not aware of the changes or is not informed, and it could impact the ability of that product to continue to perform and remain qualified. So what we're trying to do right now is develop a list of requirements by product area, couplings or fittings or whatnot, where if the suppliers make a change to certain processes or equipment, they have to notify the approving group. And if, we would review it and determine if they have to requalify the product or if it's a minor change and no qualification is required. So it depends on the nature of the change, and perhaps they made a change, but they did testing to verify that it had no impact on the qualification status of the product. We move on. So we're still working on that. And in the last 5 years, we were contacted by Boeing and Airbus, and one of the biggest problems they have during their factory building of hydraulic systems is leakage. There's requirements to assemble the hydraulic fittings and torque them up to whatever requirements are on the drawings, but all too often that process is missed and they end up with large leaks on the floor, and I'm sure this happens in the field as well. So what they're trying to do is develop a type of fitting that can be torqued up without torque wrenches, without measuring torque, but there's a visual indication that it's been torqued. And it would vastly minimize the cost and problems we would have with fluid systems not being torqued properly and leaking and slowing down production. So we have a specification that is in a development stage and it has not been balloted yet or released yet, but it's something that's in work and it will be very helpful for the industry. We are also updating with our hose assembly requirements. The original component manufacturers or the hose assembly manufacturers, they will outsource or have suppliers that are approved to assemble fittings onto the hoses and they do certain testing that's required part of delivery. But some of the testing is done on a periodic basis, such as fire testing. And there's been some debate on whether or not these distributors who are adding some value to the hose assemblies, they're putting fittings onto the hoses and putting fire sleeves on, whether or not they have to periodically do the tests that are required of the original component manufacturer. So they're building these products under license, but there's questions on whether or not and how much fire testing they should have to do, because what they do could impact the capability of the product. And we're also, under the last bullet on this chart, we're developing a qualification requirement for low pressure coupling part standards. We have all the part standards released. We're still working on the requirement specification for this. It has not been released yet, but it's something that we'll probably be releasing in the next year or so. We've delayed, mandating buying these parts to a QPL yet. So it is, sometime next summer we have in 2022 we have a extension of this requirement. So we're trying to get the specification out on this. Next chart. And as I mentioned, we as one of our missions, we continue to support performance review institutes, qualified manufacturers list, and qualified products list development. There's always activities and projects, with suppliers who want to get on the qualified products list. There are issues that pop up where a product has failed in the field or has failed during periodic testing at the supplier, and that product needs to be reviewed by this particular group within this committee to determine what actions they would need to take to reconcile the problem that occurred on their product, so they can remain listed on the the qualified products list. We also are supporting the NADCAP PRI, where we have a very, very large audit and oversight operation going on to just basically maintain oversight of the suppliers that make product that is listed on the QPLs. We're also, as I mentioned earlier, we work with the one committee works with our European counterparts to ensure that our part standards and their part standards are in line with each other. We agree with the requirements and the certification requirements that go along with that. And in recent, there's been a lot of discussions about replacement of cadmium with zinc nickel. So we formed a panel that will start meeting to discuss what products we can convert cadmium to zinc nickel. We have a lot of concerns with what impacts that would have on performance, have on torque requirements and things like that. So those discussions are ongoing. And likewise, there's environmental concerns with use of some of the types of passivation on corrosion resistant steels that are used on the parts that are have oversight from this committee with standards. So we're right now we're not making any change in our passivation requirements, but some users are becoming a lot more strict on what passivation can and can't be used, passivation type. And as mentioned by some of the other folks, we have many documents that need to be reviewed on a periodic basis to see if they're still relevant, to see if they're they could be stabilized and more or less put on the shelf and not have to be updated and reviewed every 5 years. But we have roughly 500 documents that have to go through, that are on the list of having to be reviewed at this time. So we're busy. Right now, we have about 25 to 30 open project ballots. Typically they run through a 28-day cycle, and if they have to reballot for some minor issues, they can reballot with a 14-day. But that keeps us busy. We have published about 19 documents in the last 6 months, which I believe is pretty good, pretty active. And we're also developing a qualified products list for 3,000 PSI externally swaged fittings against numerous AS fitting part standards. And so that we have a procurement specification for that, AS 4459, that we're working to, and that work is ongoing. Next slide. So moving forward, we will continue to develop that QPL for the AS 1895. It's a V retainer type coupling, low pressure, 130 to 150 psi. Used in fuel and pneumatic systems. We're always seeking out more OEM and user participation in our committee standardization efforts. So, folks are, wanting to get involved with the G3 more. As has been said, the meetings are open. You can contact myself and I'll provide that information at the end of the presentation. So I encourage you to try to get involved with this committee and learn more about what we do. One struggle we have is with, qualification activity, where we receive reports from suppliers, and we have a limited number of folks from the users and the OEMs that review this data. And we always struggle to complete the projects on time. Right now our backlog is pretty low, but we were really in trouble for a long time trying to find time to review this data from suppliers and resolve issues. There's been some pilot projects ongoing. We have not done this yet, but I would like to see us try and shorten some of our ballot times, where we have very, very minor changes to a part standard where somehow a wrong dimension got on in one of the cells in a table, and everybody kind of is in agreement that it needs to be fixed, and it's basically a quick flow to minimize the amount of work, and get the ballots out quicker to help our suppliers out and users. Succession planning, maybe not just our committee, but I'm sure many committees, there's a lot of senior folks that may be near retirement, so there's attrition, and we always need new participants that have a fire and passion for working in this area. So we need to do a better job, I know, within my committee as well as some others, on succession planning. So we have folks that are ready to take over the work that we do. So our next meeting, we meet twice a year, and within the last since March of 2020, we've had to meet virtual as a result of the COVID issues around the world. And our next meeting is going to be face-to-face in Salt Lake City, Utah, March 8th to 10th. Like I said, it's an open meeting. So anybody that is able to make it to the States for that meeting, you're welcome to attend. And that's it for our future roadmap for now. The next slide. So as I said, I'm Joe Bebby, the G3 chairman. If you have any questions or comments, feel free to send me an email. Kevin Byers is our SAE Aerospace Standards Specialist, who can help you get more involved with this particular committee and other committees that he's involved in. Feel free to email him as well, or give him a phone call. So at this time, I'll like to take on any questions that folks may have.
Thank you, Joe. I think there are quite a few questions in the chat window. Mr. Karthi Tyagarajan has almost 5 questions. I'll go one by one. The first question is for fitting QPL, that is a qualified product list. Is the test plan can be customized from the applicable procurement spec?
The test plans that get submitted, we within the QPG have come up with a standard format, I believe, for submitting test plans and submitting test reports. So I believe we have some, you know, I mean, you said customized, but I'm not sure if that answers the question or not. I know we've come up with somewhat of a standard format that we would like to see because it makes it easier for us to find information in the, you know, within the data that gets submitted, and it expedites our review time.
Okay. The next question from the same person is there any terms and definitions used in FLU -QML, Qualified Manufacturers List, QPL handbook does not have, and QPL guidance does have much detailed terms and definitions? Joe, do you want me to reread, or does that make sense?
Yeah, so I guess I'm not clear on what handbook is being referred to. I mean, there are, you know, qualified manufacturer list and qualified products list requirements that are defined within the NADCAP and PRI documents that have been released. If the handbook is the SAE G3 handbook, I know that may be out of date.
I think it's the same person has clarified, Joe. QM handbook. He's talking about QM. Is that quality management handbook?
Yeah, it's not clear to me what the QM handbook is.
So maybe, you know, Joe, what we will do is we will, I'm just seeing if there are any other questions outside of this. There's one last question. What is the lead time from the approval of test plan to QPL listing? What's the lead time?
There's a number of factors that involve that lead time. Sometimes we can have folks listed on a qualified products list within months, but there's often, you know, there's time to review the test plan, time for folks to complete the testing, assuming they have product available to test. Test report has to be submitted, then reviewed. So I would say the typical lead time is, you know, for a fairly straightforward fitting type qualification is probably 6 months or something like that.
Yeah, sure. Thanks, Joe. Again, I think in the interest of time.
Correct. And if there's any other questions, you know, feel free to email me and provide specifics. I appreciate the questions and appreciate the opportunity to speak to the workshop folks, those in attendance. Be well, everybody. Be well.
Thank you, Joe. Thank you for the insightful session on all the standards in aerospace couplings, fittings, hose and tubing assemblies. It was great. Thank you. Folks, members, I'm sure you all enjoyed and gained valuable insights on the upcoming standards and you know, what these standards comprised of. With this, this brings us to the end of all the sessions in parallel track session 2. Now let's join back to the main session 1 for the valedictory and vote of thanks. Thank you, folks. See you at the session 1 now. Thank you.